third monthly speaker series. We want to welcome Jeremy from UBC to talk about their urban freight emissions program. As Jeremy said, he's got about 35 minutes, so we're leaving plenty of time for questions. And we will be, ending around 1 o'clock, just so everyone can get back to their workday. So I'll hand it over to you, Jeremy.
Okay, great. Thank Wilma. Hello everyone. My name is Jeremy Rochison. I'm a research program manager, research engineer, scientist, jack of all trades, working out of UBC's mechanical engineering department, as well as the Clean Energy Research Center. I work very closely with Dr. Patrick Kirchen, who I think is on this call right now. Many of you may have seen him presenting at Greenship a few weeks ago. So that's sort of in the same vein as what you would have seen there. Today's presentation, as Wilma said, I'm going to give a little bit of background on our urban freight emissions program, but focus more on our marine tank-to-wake emissions data and how we think about those types of data sets. So I'll start off with a bit of background on our freight emission program. I'll get into our in-use emission measurements. So basically, why do we care about generating what I call decision grade tank-to-wake emission factors? I'll talk a little bit about our methods for collecting that data. I think someone might have their mic on in the background there, so if you could mute, that'd be great. And then after I've given a bit of background on how we think about the data and collect it, I'll sort of start talking about some actual applications. So looking at our real emissions data sets that we've collected from local vessels, looking at LNG, so that's really focused on the methane slip problem, how we can address it, as well as biofuels. And there the questions are really more around air quality, just like we were talking about with Strathcona. So things outside of CO2 like NOx, black carbon, particulate matter. And then I'll end off the presentation sort of giving you guys a bit of an insight into what our future directions for the marine research program are. So the UBC Urban Freight Emissions Program, this is funded by Environment and Climate Change Canada. It's a 5-year program, and we've just sort of ticked over the halfway mark right now, so we'll be wrapping up in about 2027. And our motivation or our mission is to generate data, tools, and strategies to help mitigate greenhouse gas emissions as well as air quality pollutants, specifically from urban freight vehicles. And so when we say urban freight vehicles, you can see the photos on the left side of the screen there. We're talking about heavy duty on-road, marine applications, and rail. And the urban part's really important because of two factors. The first being that these vehicles are now operating what we say off-cycle. So they're very dynamic operation, not really well represented by some of your standard emissions inventory duty cycles. And the other piece, like we were just talking about Strathcona, these vehicles operate near where people live. And so there's actually an extra importance in understanding the air quality component, not just the GHG emissions. So this program has a sort of a variety of different research themes, and that's what this flow diagram is highlighting here. The vehicle measurements, so sort of onboard vehicle emissions testing, that'll be the focus of today's discussion. But we also feed this data into our corridor measurements, so measuring emissions around roadways and waterways, as well as into sort of fleet level freight system modeling, looking at how pollutants disperse, and then using all of what we've learned from all these different research themes to conduct some case studies. So looking at vehicle optimization, understanding impacts of specific fuel switching, looking at policy interventions. The real foundation of this whole program, though, is in addition to these research components, is really our very active participation with stakeholders. And so we have an advisory group that we meet with regularly. They provide us guidance on how we can align our research efforts with real world problems. And it also gives us a nice conduit to sort of relay almost real time, I'll call it, research results with them so they have the most up-to-date information. Here's our research team, really just showing this to sort of highlight the very multidisciplinary group that we bring to this problem. So our team leads are Amanda Zhang and Patrick Kirchen, but we also have profs from atmospheric chemistry, from medicine, from chemical bio. So it's really a lot of different perspectives and solution methods that we bring to these problems. We also have a very large graduate student cohort. And so this is really just to highlight that not only are we generating data and tools, we're also generating sort of a workforce that's familiarized with the sort of real world problems around air pollution. And they sort of continue on our legacy after the program ends. Okay, so stepping back now and looking more about away from our freight systems, now really onto marine. If we think about how air pollution is being considered for marine, it's been sort of the same story for a very long time. So our existing fleet is a significant contributor to greenhouse gas emissions. And the IMO has recognized this and has sort of reduction targets that I'm sure most of us are all familiar with. But it's important to understand that the way we've been thinking about this is based on a very homogeneous existing fleet. These engines are sort of the same diesel engine construction. Many of the same fuels have always been used. And so the sort of emissions concerns that we have around things like CO2, NOx, SOx, maybe PM, that story has kind of been the same for quite a while. And so when we have been making decisions about investments from a fleet or port perspective or environmental policy, existing frameworks have been reliable methods to look at this. The story is changing though. So this plot on the bottom is showing sort of the difference between the existing fleet and the future fleet based on what orders have been placed. And so over half the future fleet is going to be ready to operate on alternative fuels. And so as this global fleet diversifies away from our existing engines and fuels, our decision-making processes are going to have to adapt along with them. We can't necessarily rely on the data and tools that we've used in the past. And what this really means is that as we're making these sort of long-lasting decisions and investments, we're going to have an increased need for reliable emissions data to be accessible, both again for capital investment, but really also for policy. IMO has recognized this. So I think Pat showed this in the Green Ship Conference as well, but this is the fuel life cycle label. And it's sort of, I think of it as an acknowledgement that we can no longer rely on just a single default emission factor or emission data set for all fuels to think about GHG reductions. We have to actually start thinking about actual emission factors. And so these actual emission factors, I won't get into too much detail of the different components of the life cycle label, but you can roughly think of it as the well to tank emission factor, so all the upstream production pollutants, and this is really just looking at GHG. So you'll see that's always measured in grams CO2 equivalent per megajoule fuel. And to that, we add the tank to wake emissions. So what comes out the stack of the vessel. And that'll be very sensitive to the types of fuels and the types of engines that are being used. And that tank to wake piece will really be the topic today. Adding the well to tank and tank to wake gives you this well to wake emission factor, and that's ultimately what we're caring about when we're talking about these emissions. We want to understand the overall impact of our operations and how to minimize it. So taking now more of a local lens, we have a variety of different fuels that we can look at to reduce our carbon intensity. So this plot here is sort of looking at using data from the BC Low Carbon Fuel Standard and measuring each of these different alternative fuels in a grams of CO2 equivalent per megajoule fuel. So massive emissions per unit of fuel. Each dot represents sort of a specific fuel path. And so each one of those dots in a marine context is a well-to-wake emission factor. The difference in these dots, and you'll see some of them have like a really large range, almost all of that is due to basically different upstream pathways, so different well-to-tank emission factor values. So for these alternative fuels, especially biodiesel and renewable diesel, the manufacturing process, the transportation process, all of that has a significant impact on the actual life cycle carbon intensity. However, what's not actually captured in these is the tank to wake. So except for a very small amount of special cases, default tank to wake emission values are used to generate these carbon intensities. And so this raises two important questions from our perspective, which is for these future fuels, how reliable will these standard tank to wake emission factors be? Can you use that to make decisions? And now that we're concerned with air quality, especially around urban freight areas, will these static tank to wake emission factors be reliable there? Can you make decisions based on that? So today's talk will really be looking at the fuels that are most relevant to us right now, which is the biofuels and the LNG. So again, questions, how well do single tank to wake emission factors work? Another way of saying that, does the amount of emissions produced, so for example, CO2 in kilograms per hour shown in this plot, does it scale with the consumed fuel or the engine load? So that's the x-axis there. And if we look at CO2, and this is real data measured from a local vessel a few years ago, we see a nice straight line. So the massive emissions that comes out of this vessel divided by the work produced or per unit work produced is constant. The question is, how well does that hold when we look at other pollutants? So other fuels are going to have other pollutants of concern besides CO2. Now the story gets a lot messier. So we have methane on the bottom. That's another important GHG emission. On the right, we have NOx and CO, which are obviously important air quality pollutants. The two sets of lines for each one of these, it's actually the same vessel, just the engine is being recalibrated. But what you can see, the real takeaway here, I don't want to get into the details, is that there's no straight line that you can draw through any of these. And any vessel actually could have multiple different calibrations or impacts. And so this really draws into question, how is it that we can make decisions either on air quality pollutants or GHG emissions confidently and make investments based on that when these all other air pollutants don't really follow the same emission tank to wake emission factor rules that we've relied on with CO2 and conventional fuels. And so that's really the motivation, the objective of our marine emissions programs. It's to generate decision grade data for tank to wake GHG and air quality pollutants relevant to the maritime sector and specifically relevant and useful for urban and port settings. And so this is for standard fuels, the existing fuels, as well as the currently in use low carbon fuels. And eventually we'll be moving towards future fuels, helping get some early data on these other fuels that are being considered. When I say decision grade, and I'll use that term a lot in this presentation, what I really mean is that the data can be used confidently. The data is robust and can be used for planning and policy development or technology selection, really answering specific questions. And to us, this means that it includes quantified uncertainty. It takes into account the real world variability of these vessels, and it also has some consideration of the operational impacts. So our approach for developing decision grade data, we can think of this in terms of the data quality. Obviously, we want the maximum quality possible, but we have to weigh this against the cost of collecting it. So because we're talking about real world systems, it's quite expensive to go out onto a vessel and change their operations, allow them to install our equipment. And so we have to weigh our data collection methods, both in terms of the outputs, but as well as the cost of the inputs. And so the first thing we can think about here is default or published emission factors. This is sort of the standard approach that we've talked about before. Very low cost, but potentially some cost in terms of making the wrong decision. The data quality doesn't really give you much opportunity to make improvements to your process either. The next thing you can do is looking at in-use sea trials. And so here we actually go out onto a vessel of interest. We're in the real world now, so we have the data we collect is relevant to real world operations. Or we could do emissions monitoring. So rather than doing dedicated sea trials, we install equipment and leave it to monitor for a long period of time. This has sort of a wide range of data quality potential, depending on the type of equipment you leave on board and how well you qualify. And I'll talk a little bit more about that in a bit. Starting off with the in-use sea trials, though, the standard approach is sort of following IMO NOx technical code, which is designed for validating engine performance. It's not designed for generating new emission factors. Our approach is a little bit different than this in that it combines these sort of steady state sea trials, maybe in a slightly more expensive way, but we combine them very intentionally with emissions monitoring. And we do this in a way that's designed to match the actual use case of the vessels that we're studying, to validate the instrumentation that we can use for monitoring, and to really generate something that we call effective emission factors. And these are really the link that allows our tank to wake emission factors to become more decision grade than just sort of your standard emission factors you might generate. So we've been operating this program for, I think, 7 or 8 years at this point, all in local applications. We've had good fortune to be able to collaborate with some great partners. Some of the vessels that we've measured on are shown here, along with the different types of fuels we've been able to measure. And I just want to highlight sort of the routes that we look at, just to highlight that these are operating near where people live. So this is those urban components again, and they're also going to be very dynamic with different navigational constraints through things like Active Pass or the Fraser River, or different traffic happening through the Georgia Strait. And so all of these considerations put sort of an extra emphasis on better understanding of air quality pollutants, but also really capturing the impacts of those dynamic duty cycles when we talk about the effective emission factors. So what does it look like when you actually do a sea trial? What is our instrumentation that we bring? I'll try and bring up my pointer here. So we have basically, we'll go into the engine room, install our equipment, and we'll bring a series of different sample probes directly into the exhaust of the engine. Sometimes we're fortunate to have an existing access. Sometimes we have to ask very nicely for our partners to install some ports for us. But we typically have a couple of different ports that go in there. Those ports will lead through an extractive sampling system, and that sampling system will have a series of different instruments, sort of with different capabilities, each of them measuring in parallel. So we'll have a black carbon instrument typically if we're measuring biodiesel, and we'll always have a couple of gas phase instruments here. Those instruments all have very different costs and capabilities. So for example, we have laboratory grade instruments, certification grade instruments. These are all very difficult to bring, but they also bring a certain level of quality that we can rely on because we have calibration standards. The other thing we do in parallel to this, though, is we bring a monitoring system. And so that monitoring system is operated in parallel to the high quality, what we'll call it high quality sea trial data set, but it's a much lower cost instrument set. This is just sort of a photo of what that looks like. So we'll set up for sea trials. The vessel will be put on whichever fuel we're interested in for some period of time beforehand so that we're confident that we're looking at the blend that we intend to. And then we install our equipment somewhere in the engine room. In this case here, you're actually looking at the Fiddly 6th deck of the Queen of Oak Bay from BC Ferries. The exhaust is over here, and so there's actually some ports kind of located up around here. And we have a series of sample lines that come down from there and extract exhaust gas and lead to our different analyzers. So we have a black carbon instrument here. We have our certification grade gas emission exhaust gas analyzer here. This comes from the on-road heavy duty sector. This is our laboratory grade instrument. And then over here, we have our monitoring instrument. So this is a nice application where you have lots of space. However, sometimes we're operating in the engine room and it can be quite intrusive. And so this is not really a viable approach for doing all sorts of emissions measurements. It's really for dedicated cases where we're trying to do detailed characterizations. So we'll measure each fuel. We'll do sort of sea trials during commercial operations. So as they're doing the crossing for BC Ferries, we'll get them to hold certain loads for 20 minutes at a time, get a steady state measurement, move to another load, get a steady state measurement, and repeat until we sort of scan the full operating space of the vessel. We'll do that for each of the fuels we're interested in. Typically, we're looking at a baseline fuel, which will be your standard marine diesel or something similar, and then maybe a biofuel or an LNG operation as a comparison point. After we've done each one of those sea trials, we pack up all our equipment and we leave. But we typically try to leave just our emissions monitoring system. And so that monitoring system will live on board for weeks or months and continue to collect data. And in this case, this is a NOx sensor used for biofuel analysis. But the great thing is that NOx sensor, that monitoring system, was living beside the sea trial data set through all of the sea trials. And so we actually generate this large data set of in-use validation data to understand exactly how well that system performs in the real world for real fuels. So I'm showing some plots here showing how well that comparison can work. The takeaway from these plots is the x-axis is the performance of our certification grade instrument. The y-axes are the performance of our other instruments, and the one we want to look at is the monitoring instrument here. And the takeaway is a straight line close to this black dash line means that the instrument will provide you about the same conclusions as the certification grade instrument would. And you can see this is for a series of many different data sets and measurement days that we've done. And what that means is the data that you get from that monitoring test set is going to give you the same sort of conclusions as if you'd left that certification grade instrument that's very expensive on for a series of months. One important note that one takeaway that we've learned over the years of doing this is that doing the validation in real engine exhaust is critical. So there's a lot of low-cost sensors that we've identified that we've tested and work very well on calibration gases, which are dry. They don't have particles in them. However, when you bring these onto real engine exhausts, they perform differently depending on the fuel sometimes, and they also can be wildly wrong under certain conditions. And so doing this validation process in the real world on real exhaust is a really critical takeaway. So that was a little bit about the methods that we use. And now the next part of the presentation is really looking at the tank to wake emission data that we generate and really looking at two of the case studies that are relevant around here, which is looking at biodiesel as drop-in fuels and LNG, of which there are a variety of vessels that operate on locally. So with the biofuel, this is an interesting one because it's a drop-in fuel. And so now you have engines that weren't designed to run on biodiesel being tested with a variety of different blends. How do the air quality pollutants such as NOx, PM, and black carbon change with those different engine types and those different fuel blends? And then with LNG, the question is a little bit more about the GHG reduction. So with LNG, we get we always get an air quality improvement, a very significant one in terms of NOx, black carbon, and PM. However, the GHG reduction is a question, and that really comes down to the unburned methane, the methane slip in real world conditions. And so we want to understand what strategies exist to minimize that slip, of course, and how do those dynamic off-cycle duty cycles that these vessels locally have impact those methane emissions. And so the vessels that we have to answer each of these questions have different features of them that kind of help paint a sort of a broader picture of what the considerations are. So I'll start off with the LNG vessels and some sea trial data we have for methane slip. So the data shown on the right here, this is emission factors for methane, so grams of methane per kilowatt hour. And we've measured it for 3 different vessels, the black, the red, and the blue. For each vessel, we also looked at engine manufacturer supplied recalibration that was designed to reduce the methane slip. And so that's what you'll see, that there's 2 curves for each plot. Original means this is how the engine was delivered. Updated means this is how the engine performed after the fleet operator requested that the methane emissions be reduced. It's unfortunate that you have to ask for methane emissions to be reduced, but that's the reality. So there's some general takeaways that you can see from these plots. The first is that for each of these vessels, each of these 3 vessels, the methane emission rate can increase by sort of an order of magnitude as you go from high load to low load. And that's true for each one of them. What that means is the duty cycle, whether you operate at low load a lot or at high load a lot, will be very important for your real world GHG emissions. The second thing is these upgrade packages that you can get for these engines have sort of quite a significant range of effectiveness. So in the case of the black lines and the blue line, you can see that the updated curves are significantly lower for large portions of the engine operating range as compared to the red curve, where you basically get no benefit except for at the very low loads here. And so it leaves you with a question: is if we're trying to come up with a single emission factor for methane here, if you're not able to do these measurements yourself, stacking them all on top, you actually have a very large range of different emission factors that you could reasonably select. And this leaves you with the question of which one is actually the right one to use, which is the most accurate to you. And that information isn't exactly clear, even though you have these data sets. So what would be the typical way to sort of combine this and generate a single tank to wake emission factor? The IMO E2 cycle, which is shown here, this is just sort of a weighting scheme that's used for engine certification. So what it says is you take one of these curves that can be from a measured or from the published data, and you just do a weighted average of it at specified loads. So that's 25, 50, 75, and 100%. And regardless of how the vessel actually operates, you take a weighted average at those loads, it'll generate a single emission factor, and that's our output value. It doesn't take into account the real world duty cycle. And so our approach with effective emission factors is to take these curves, but then actually also combine them with days of sailing. So each one of these blue dots shown on this plot here is 1 day of sailing for that specific vessel with our sea trial data applied. This allows you to generate what we call an effective emission factor, so you can take an average of all those different days of sailing. but it also gives you a sort of a spread of how much variability you get in those emissions. And that's really because each day of sailing has different constraints. There's more or less low load operation, for example. And this is important to understand. The other thing that you can see from this is that it gives us very clear answer in some specific questions like, are these upgrades recommended for my application? So for example, on vessel 1 and vessel 3 over here, you get significant benefits, while for vessel 2, you basically get no benefit whatsoever. And so this is an important thing, that combining both the duty cycle and the real world emission rates is important to help make fleet operators make these types of decisions. The other thing it enables us to do is sort of look at the maximum range that these vessels could potentially achieve in terms of emissions performance. So this on the right, on the left here, the opportunity would be combining theoretically the best engine that we've tested along with the best duty cycle. And you can see this gets down to a very, very low emission factor here, significant benefit in total GHG versus diesel. Or there's a potential risk of, if we had a vessel that had the worst of the engines that we tested and happened to be constrained to the most challenging duty cycle, we now have an emission factor that's significantly higher than anything we saw from the real world cases. Any of these effective emission factors are realistic and reasonable to expect. And so it's really on the fleet operator to understand their operation and take steps to actively mitigate GHG emissions from these vessels. So it's through duty cycle optimization, or through technology upgrades like these calibrations, or ideally both. Okay, so that was that sort of the quick story of LNG. Moving now into the biofuel blends. What we talk about locally, and I'll only be talking about sort of the FAME biofuels, fatty acid methyl esters. So these are coming from soybean, canola, or waste cooking oils typically. I'll refer to B5 as sort of our standard fuel. So that's nominally a 5% bio blend with 95% petroleum diesel. And then we'll look at blends of B50 and B100 to sort of help understand the trends of emissions as you increase the fuel blending. So now we looked at methane emission factors before. Now we'll look at NOx emission factors. So this plot is looking at NOx grams per kilowatt hour, and as a function of engine load here. So this is all for one vessel, one of the passenger ferries we looked at. This is an older vessel, tier 0 engine with direct drive to the propellers. And what we can see first with, the red curve being the B5, B50 in blue, and B100 in black. Indeed, the expected increases in NOx with increasing biofuel blend can be measured. However, again, we see that there's a significant sensitivity to the engine load. And we also start to see that these error bars can be significant for certain parts of the operating range. So we see that there's a range of different performance that we've measured in the real world at any given engine load. And this means that if you're trying to understand what is the relative change or make a decision based on some incentive, you really have to acknowledge that these aren't just single numbers that are perfectly replicated all the time. These data points were actually collected on the same day, just with the vessel operating in different directions, so different gearbox loading, and that was enough to generate significantly different emission factors. We can look at other vessels as well, so newer vessels, and this is a tier 2 vessel now. Slightly lower NOx emission rates. You can see the scale here is a little bit lower, but we also notice that the shape of the emission curve is much, much different. This is because it's a tier 2 vessel. It's being tuned to reduce NOx specifically at these limits. So you can see where those red lines are. Those are the 25, 50%, 75%, 100% load points I mentioned from the E2 test cycle before. And we can see clearly that the engine has control parameters used specifically to reduce the emissions at those points. We can also notice that the variability in the data points is a lot tighter on this vessel than it is for the other vessel. That is mostly due to this being an engine that operates as a genset. So the engine connects to a generator, and that generator drives electric drive motors for the propulsion. This removes all of the sort of drivetrain variability that can impact the engine load by modifying the engine load dynamically, even while you're nominally at steady state. And so the thing to think about with that is, looking at the difference between these two curves, we actually have a lot more confidence in the difference between these because the variability is so much lower. than we do with these ones, where these error bars start to overlap in certain parts of the operating range. And so it just goes to show that not all data is created equally, and it really depends on each vessel's application. Another way to look at this data and sort of combine it for multiple vessels at once is to sort of look at the relative changes. So instead of absolute values of NOx emissions, I'm now showing a delta NOx, so a change in NOx as a percentage. And so that's sort of, you can imagine that for these B50 cases here, this is the NOx emission rate at B50 divided by the NOx emission rate at B5. And what we see is, you have an increase in NOx emissions. It varies quite a bit. So you see sort of 10 to 15% for one vessel, 15 to 25% for another one here. Generally increases for the higher blends as we expect, but then we have a much lower or much less significant NOx penalty for that tier 2 vessel that we saw here. Other thing to note is that you're starting to see that these curves have a few different other features that are worth noting. So we're actually looking at the real operating range of the vessel. So rather than talking about, like, for example, this vessel, what its 100% load NOx emission rate is, that vessel never operates there. And so that engine operation point isn't actually relevant to the real world questions you would be asking. The other thing is that we have these sort of shaded regions around each of these curves, and those are indicating what the measurement confidence is, or the uncertainty of those measurements. And so one way to think about that is where these start to overlap with each other is an area where, if your decision is based on, is this fuel giving me higher or lower emissions, this is a region where you need to acknowledge that your data may be not enough on its own to make that decision for you. This is something that we find is really lacking in a lot of the discussions around emission factors, and it's really an important message that we're trying to get across to people who think about these things. So all of this is still sort of steady state emission factors. The vessels, as we mentioned, don't necessarily operate at steady state. So the next thing we can do is turn to our monitoring data. So this is now looking at effective NOx emission factors over several months. And so we have a NOx monitoring system installed on this was a articulated tugboat operating on B100 for almost an entire year. Each one of these dots here takes basically the total measured mass of NOx for that day, for that sailing, and divides it by the total fuel consumed. And so you get this emission factor and NOx per megajoule fuel here. But because we're measuring on a day-by-day basis and not relying on sea trials, you start to get these long-term trends in the emission rates. So it's no longer a case of our sea trial data gives us the static number that's valid at all times. If we actually go out into the real world and see what really happens, the vessel's daily operations has some variabilities. That's the width of this bar here. But throughout the season, things like temperature changes or fuel supply changes also cause significant changes in the real world emission factors. We can also do some interesting things like looking at in-tank fuel blending without actually having to go out and install new equipment. So because we did the validation of these instruments that were used to measure this along with our sea trials, all we have to do is get the fleet operator to do some in-tank fuel blending to see what would your effective emission factors be if you did a B5, B100 blend. And we also looked at sort of a temporary swap to B5 just to see what the real world difference was if we go compare these data points here for real world operation to these ones here. The other pollutant that we care about is sort of on the particulate matter. So one of those is black carbon. I'll talk just sort of briefly about this, but this is that same change in black carbon as a percentage relative to the standard fuel, which was B5 for these cases, for all the different vessels that we looked at. And so now the y-axes are negative and very significantly negative, which is great. Black carbon is a strong climate forcer as well as a significant health concern for people inhaling it. And as we go to much higher blends, so B100 shown here, basically all the vessels that we looked at, regardless of tier, showed a really significant decrease in the black carbon. So this is unlike the NOx emissions, which were sensitive to the type of engine. The black carbon emissions, the reduction that you get with that seems to happen regardless of which type of engine you're operating. Just to give sort of more intuitive feel for what this black carbon is, this is the actual soot that you see coming out of the engine when it's operating, usually when it's dynamic operation. So these two videos on the right, these were controlled dynamic tests. So the loading on the engine here goes from idle, unengaged propeller, and then we basically slowly ramp up to full load to sort of simulate how the vessel would be operating as it leaves berth. On the left here, the B5 case, you can see pretty clear black cloud. And then with the B100, it's really, really hard to see from this video anything at all. And so we've had feedback from some operators that this plume of smoke that comes out here, especially operating in the North Vancouver harbor area, this is actually a major concern for some fleet operators. And so it's an important benefit to get rid of these visible emissions. But the point, something important to note about those is that's only the black carbon, that's the visible part. We also have total particulate matter. And so I'll just touch this very briefly. It gets pretty complicated, but the total PM is both that black carbon component, the soot that we saw, but it's also this organic carbon content. And that's not something that you see visually, but it's still additional massive particles that can be fuel or unburned oil or a variety of different volatile components. So this is just a slightly different way of measuring those particle emissions. So this is still black carbon. This is just to show that this new measurement or data set tells us the same story as we saw in the last couple of slides. When you switch from B5 to B100, the black carbon reduces significantly. If you instead switch to looking at the total particulate mass, your black carbon, your total per PM from the B5 fuel, it goes up a little bit because you now have this little component of potentially unburned fuel or oil. But if we look at the B100 now, we actually have a significant increase in the total particulate mass. This is something that we're still sort of working on actively to understand the implications of this, but it's really important to understand that as we get to these other types of pollutants that we're less familiar with discussing, the story about how we weigh them against each other becomes a little more nuanced, and it becomes more important to understand how they actually operate in the real world. So just sort of to wrap up some of these marine emissions takeaways, on the LNG vessels, there's GHG benefits, but they're really, really dependent on the vessel's duty cycle and the engine technology that's installed. It's possible to have very effective or much more effective methane slip from these engines, but it's really relying on the operators to be proactive. You can't just buy a vessel and assume it's doing the best possible job. It requires looking into it, and we would argue that having data to arm you with that discussion is one of the best ways to approach it. On the biofuel side, we saw from the LCFS that there's very significant GHG reductions possible with these biofuels as well as HDRD. However, this has to be weighed against air quality considerations. So we see NOx emissions increased for all of the vessels that we looked at. The significance of that increase really was dependent on how new the engine was, what engine tier it was. The black carbon, the visible part of the exhaust, that was really very, very significantly reduced for all tested vessels, so irrelevant or irrespective of the engine tier. But we saw that the total PM, on the other hand, was increased just for the one vessel that I showed data for there. The high level takeaway that I would really make, though, and this applies to all marine fuels and especially in urban areas, for emission factors to be decision grade, which I would argue is sort of how we should start to think about these types of data sets, they really have to reflect vessel duty cycles in all case. They have to reflect the real world variability, and they really need to have some comment on how much uncertainty there was in those measurements, because that can really change how you think about using them for decisions. Our approach for doing this has been to combine in-use sea trials along with sort of long-term monitoring approaches. And so this gives us both the operational context, but also sort of more of a robust statistical understanding of these emission factors in real-world cases, which makes them suitable for decision-making like planning or technology evaluations. So my last slide here, I'm just going to touch on sort of our outlook for the emissions measurement program, again, in this sort of space of data collection and data quality. The first thing is sort of sharing some of this data that we've collected. We've been very active on the measurement side. We're now really starting to think more about how do we share this data with people that can use it. So this is getting it put into default values, but also sharing it in forums like this, multiple different ways that suit different stakeholders. We're going to continue with our in-use sea trials, but we're now thinking sort of really more looking towards the future fuels, so methanol and ammonia in particular, as well as maybe some conventional fuels with engine types that we haven't looked at yet. So, for example, biofuels on low-speed two-stroke engines would be of interest, and we haven't looked at those yet. And then the last piece is really sort of building out our emissions monitoring capability. So I showed we have sort of a good handle, or we're developing a good handle on NOx monitoring. We'd really like to sort of extend this capability to other pollutants and emissions of interest. So that would be methane, methane slip, as well as getting a better understanding of that particulate matter and black carbon problem that I spoke about with the biofuels. We're also looking at sort of extending some of these to other applications. So I mentioned rail is one of those. So with that, I would like to thank you for your attention, as well as a variety of funders and many collaborators that we've had, and especially the vessel crews that have made all this work possible. Thank you.
Thank you, Jeremy. I think there's a number. Let's actually go to questions from anybody on the line right now, and then there's a few questions in the chat that you can address as well.
Sure.
So, are there any questions on the line, or should we go straight to the chat?
Okay, I mean, I can go straight into the chat, I guess.
Yes, let's go straight to the chat.
Let's see. Darren asks a bunch of questions. First one, have you been able to measure emissions on deep sea ships sitting out at anchor and or in port? No, that's a great one. That's actually an area that we have highlighted as one of our next steps. The local operators are a lot easier logistically to coordinate with. We're interested in anyone who is able to get us access to one of these deep sea ships. We know there's a lot of interest from Environment Canada, for example, on how the idling of these ships in port could be impacting our local air quality. So as of yet, not yet, but something we're definitely interested in. Are your studies being considered for green shipping corridors? Not that I'm aware of yet, but that's an interesting angle that we should consider. I might just do a sneak attack on Pat Kirchin here. He's on the line, maybe listening, maybe not listening. He may have a comment on some ideas of if we have any collaborators that have talked about green shipping corridors.
Yeah, I'm sneaking and listening. Thanks, Jeremy. Great presentation and great questions. Thank you, Darren. In terms of directly feeding a green shipping corridor study, no, not in that sense. But we're working to get the data out as much as we can, particularly for the new fuels. So the methane slip, that's a great example of that we've been sharing as widely as we can. But a lot of the green shipping corridors where you're looking at lower carbon intensity fuels, those data sets don't exist yet, minus now the biofuels. So I'm going to echo Jeremy's call. If anybody has connections to vessels or operators that are using and exploring these alternative fuels, in particular methanol, that's one that we're targeting right now. We'd love to generate data sets that could be used for those sorts of things. With that, I'll pass back to Jeremy.
Sorry for the hot potato, Pat. Right. And then the last question there was, have operators adjusted their services to reduce GHG emissions based on your site? So yes, particularly on the methane slip, so the LNG vessels. On those, the freight operators were able to, they were sort of over capacity on engine power. And so they were able to switch from 2 engines operating at part load to 1 engine operating at full load. And that moves you along that curve from sort of the lower load emissions up to the high load emissions while maintaining service. For some of the other operators, particularly the passenger ferries, the operations are a lot more constrained in terms of scheduling. And so we haven't yet been able to apply them directly operationally, but there's some recommendations there that we have that we think could be done. Any other questions? I have a question maybe for the group from my side. So as I was mentioning, one of our mission statements is to be able to actually share this data in a useful way for a variety of different stakeholders. I am still trying to get a grip on how do we communicate this data in a way that makes sense, but doesn't lose any of the important nuances around uncertainty or operations and things like that. So if anyone has comments on, did this make sense in the way I presented data or spoke about it, or any recommendations on way that can make it maybe a little more accessible for not an academic audience, but more of an industrial or non-expert audience, that would be really great. Or if you want to email that to me afterwards, I would appreciate it. I nailed it. I take from the silence that I did a perfect job. Thanks, Darren.
Yeah. No, I mean, I think people will mull it over. What we'll do, Jeremy, is we will be sending this out to linking it out to the greater audience from VMCC and the Greenship participants. So, if you've got requests that you would like people to come back to you with, why don't we tag that on as a note?
That'd be great.
And have them get back to you directly on this.
Okay, yeah, that'd be great. I appreciate that.
Okay.
Thanks, Greg.
So we ran this very efficiently. So why don't we, give people back a little bit of time to finish lunch before they have to head back to their offices.
That sounds good to me, yeah.
Thank you, Jeremy. We will be, as I said, putting this on our site with open access at this point in time, once we get everything together. And our next event is scheduled for January, and we'll get back to everyone at VMCC with dates and the presentations. But thank you, everyone, for your time.
Thanks all.
Take care. Bye-bye.
Thanks, everyone.